没有，只是他等一下。
Yeah. Okay, now let's begin our this kind of exciting technique. So again, now you should be able to look at this again. This is the easiest way to solve the control gain using what we call pole placement technique. All right. Now, here I just show you the state estimator. Assume you have a G like a 0, 1 here, and A bar equal to A plus GC. As a matter of fact, the pole placement technique can also used to solve the observer gain. So this is what we call observer gain. And this, I have a name called that B here. The reason why we call that B is the following. If I have a G01 like that, and A bar equal to A plus GC, and this A is the A shown in last slide, with delta T equal to pi over 2, and then A plus GC, then A is 0, 1, minus 1, 0, plus G is 0, 1 here, 0, 1 here, C is 1, 0, 1, 0, then A bar equal to A plus GC will become 0, 1, 0, 0. My A bar square, if we put in this A bar square, becomes 0, 0, 0, 0. That means the estimate state will converge to the true state in 2 steps. This 2 in 2 steps. So regardless of what your initial condition, then the estimate state will converge to the true state in the 2 steps. So this we call that B. That B means in 2 steps, then it's just exact the same as true state. Of course, in practice, there's no such that B observer you can get. This is only in theory. Assume that your A matrix is perfect. Your C matrix here is perfect. That means your open loop state matrix A is perfect. Your output matrix C is perfect, and which won't be the case in real applications. So you need to be aware of the practical problem. So observer equation here, if you look at this carefully, then I have a G is there, and then Y hat is my estimated output. The Y without hat is your measurement, your true measurement. So this is the estimated state equations we call observer state estimator. So you can estimate your W hat, you estimate your W dot hat through these equations. This A01 minus 1, 0, and 1, 1 is my B matrix. That's my B matrix, 1, 1 U, plus 0, 1, that's my gain G here, 0, 1, so my gain 0, 1, and Y hat K minus YK, and I know that you already done some homework, and also prove that this estimate state will converge to the true state regardless of what initial condition you assign to it. All right, and that's true. So in real applications, we do need discrete time state estimator. Now, then how can I get this G matrix. Now, how can I get those? Of course, 2 by 2, it can easy to do. For more than 2 by 2, 3 by 3, 4 by 4, no, you cannot do that. So for more than that, there are also other technique allow you to compute the observer gain G. All right. So observer gain and feedback gain, they are dual. In other words, the same technique used for control gain computation most likely also available for use to control, for use to compute your observer gain. All right. And but in this class we focus on the all right, we focus on the control gain. All right, so this is real applications. Assume you have y equal to w, and this is your the state you measure. You don't measure your dot, you measure your displacement only. Then in your computer, you need this observer state estimator, we call state estimator, to estimate your W hat and estimate your W dot hat. Now you might argue, say, oh, well, why do I estimate W hat? I can just use W here. True, you can do that too. But normally, we use the W hat instead of real W. Why? Because in real W here, in practice, you do have some noises. You do have some uncertainties. Your W, your sensor, you do have some uncertainty for your sensor. Even you measure the W, that W may not be the real W either, because your sensor has some uncertainties. Your sensor has imperfections. Your sensor may not be able to give you a very good estimate, very good measurement. In that case, you rather use W hat than W. This W hat, through this gain G, they do have an effect to filter out your noises. Understand? So this estimator is like a filter. So if you have some measurement error, your estimator will be able to clean up some of your measurement errors. Understand? So in real applications, what we do is we fx hat is my u, and so this x hat is this mean W hat and W dot hat. So you really feedback the hat, not real W and W dot. Understand? Any questions? No more questions like this? Okay. The message in these slides is that normally in real applications we do need state estimator for the full state feedback like this, because a power placement technique is a full state feedback. Means you have to have all the state informations. If you don't measure some of those states, then you have to depend on your estimator to estimate the states for your feedback. Understand? Okay. Now, let us look at the real. Now, we come to the real power placement technique. I'm going to show you. You can listen carefully, because we have to use a null space concept. The full state feedback. Look at it. Full state feedback means my U equal to FC means continuous time. BC means continuous time. FCX. Now, this FC is the gain. I want to show you how to compute this gain. So full state feedback, the closed loop system, that's the open loop system. My closed loop system is become this, right? X dot equal to ACX plus BCU. U is FCX, so BCFCX equal to parenthesis AC plus BCFC parenthesis X. So this is my closed loop system. This is my open loop system. My open loop system, the state matrix is AC. The closed loop system, the closed loop state matrix is AC plus BCFC. Now, AC is giving. BC is giving. FC is the matrix to be determined. All right? Okay. Now we are not talking about 2 by 2 matrix anymore. This is more than 2 by 2. Can be any dimension size. 100 by 100, 10 by 10. Of course, in real application, nobody really control 100 states. That's too many. Yeah, but control 5, 10 states. That's normal. All right. So for this one, assume we have the kth closed loop eigenvalue we call lambda k. The kth closed loop eigenvectors we call phi k. So x equal to this. I think this is called we call psi k, right? I think this is not phi. Phi is another shape. This is psi k. The E lambda kt. Assume my x is, the solution is psi k E lambda kt. Psi k is the closed loop eigenvector. That's this closed loop eigenvector. All right, that's my x. This is my x here. And let's assume my x equal to a psi k exponential lambda kt. You read, did you remember that I put a set of slides in the website. I show the eigenvalue, eigenvectors. Do you remember that? Remember the notes I put in the website. I show you the eigenvalue and eigenvectors, and how can you solve the differential equation by eigenvalue and eigenvectors. I think you need to refresh your memory about that. Then, if I sub into here, sub this x into here, x dot will be lambda k psi k E lambda kt equal to AC plus BCFC parenthesis, then x is psi k E lambda kt, right? Any problem? You need to understand, you need to follow me, otherwise you will get lost soon. Now, if I do this, sub all my solution into here, then I will get these equations. Now I move my left-hand side is to the right-hand side, then this becomes AC minus lambda ki plus BCFC parenthesis and psi k E lambda kt equal to 0 vector. This is 0 is not scalar, this is 0 vector. Any question about this from here, this step to that steps? From this to here, any problem? No? You can follow me, right? We just move this to the right hand side, or move to the right hand side equal to 0. So this is become minus lambda ki, and I have psi k e lambda kt, psi k e lambda kt, right? All right? Now look at this eigenvalue problem. That's my eigenvalue problem. Because the e lambda kt won't be equal to 0. So my eigenvalue problem will be, take out this e lambda kt, then that's my eigenvalue problem. I have AC, that's my open loop state matrix, and lambda k, that's my eigenvalue, closed loop eigenvalues, and I have BC and FC, and BC is given, FC is to be determined. FC is the gain we want to compute. Agree? Any problem about this from this step to these steps? Any problem? Okay. By the way, keep in mind, AC always real matrix. For real system, the open loop state matrix AC is a real matrix. But lambda k, normally they are complex. I already show you, right? Lambda. I give you complex eigenvalues. Normally they are complex. BC is real because that the input matrix has to be real. That's the system input matrix. FC is again has to be real too. You can have a complex scan. How can you have a feedback complex scan? U is a complex number. How can I have a control force which is complex? You cannot do that. So, in the whole system here, we have AC is real, lambda k will be complex normally, BC will be real, FC will be real. This eigenvector psi k is also a complex vector. So keep in mind, now this eigenvalue problem is a combination of complex value and also real matrix together. But don't worry about that because you are not the one going to compute the complex eigenvectors. The software will compute it for you.
Lambda k, we got lambda k from this.
Lambda k is a closed loop eigenvalue, it is desired closed loop eigenvalue. This is lambda k here. As a closed loop eigenvalue, we can assign, just like what I show you in earlier. This closed loop eigenvalue, you can assign eigenvalue for it. Of course, you gotta be careful. When you assign, you want to assign to be on a stable region, right? Yeah. So you can assign the closed loop eigenvalue for your system performs. So keep in mind, I keep saying that AC is a real, it's a system matrix, it's given. It's given. Lambda k here is the desired eigenvalues. And BC is given. Based on these desired eigenvalues, I want to compute FC. So, now the question is, there is only one matrix which is unknown. I mean, FC is unknown. The FC is the one we wanna compute, right? All the others are given. Of course, the psi k is the eigenvector of your closed loop eigenvalue. Okay, inside these parentheses here, only FC is known. All the others are known. Any questions? Yeah, just remember I show you the simple example. I show you the desired eigenvalues, right? That means my cross eigenvalue, I can have my desired eigenvalue for this one here. All right, that's the freedom you can use to choose. So this inside this parenthesis, AC is given, that's a system. Lambda K is the desired one, is the one you want to have. BC is given. FC is the gain you want to compute. Any questions? No? Okay. Now I call key equation. I mark in red. That means important. Now if you look at carefully, this eigenvalue problem, I can rewrite it in terms of these equations. All the line, AC line, lambda K is the one you desire. BC is 9. So I put all the line together. And 9 together on the right hand side. And this is unknown. AC minus lambda K times I times VK plus BC FC psi K parentheses equal to 0. So these two equations are identical. These two equations are identical. You can follow me. Do you understand how I change from this one to here? I see. I give you midterm exam. Some of the people, some of the students misunderstood. There's a space here. That means this is a matrix. That's another matrix. This is square matrix. This is not square. How can you then multiply them together? You cannot do that. Understand how this becomes that? If you don't understand, you will get lost. You won't understand any further. Do you understand these steps from here to here? No problem, right? Do you see the differences now? Look at that. I have a matrix AC minus lambda K I. I is identity matrix. Then I have another BC matrix here. So this matrix is a Y matrix. AC is square matrix. AC. Lambda Ki, this is also a square matrix. And then I have another matrix here, BC. So this one, you have more columns than row. Agree? You have more column than row. And if you have more column than row, and then I times this a vector. This is a vector. There's a matrix times a vector equal to 0. That means this vector is a null space of that matrix. always exist. Because you got a more column than row. It always exists in null space such that this equation is satisfied. In your exam, I give you only 2 by 2. Right? I give you B, which is only 2 by 1. Then I ask you to solve the null space vector, which is function of lambda, right? So now this is where the null space vector come out now. I have a matrix like that. I always can find a null space vector, the basis vector, such that this is equal to 0. Multiply equal to 0. Okay. Now, each lambda k has its own null space vector. K is the eigenvalue. For 2 by 2, how many eigenvalues you have? 2. For 4 by 4, how many eigenvalues you have? 4. And they always double. So it's either 2, 4, 6, always even. It won't be odd. Right? And again, eigenvalue always come with complex and complex conjugate. All right? No more question, right? Okay. The key equation. If AC is 10 by 10, how many key equations you have? How many eigenvalues you have? 10, right? So you're supposed to have 10 key equations. Agree? Because K can be 1, 2, 3, 4, 5, 6 to 10. However, if they come with a complex and conjugate, then you can count only 1, because a complex eigenvalue, the key equation will come back eigenvalue is conjugate. It's also this key equation too. All right. So this is dimensions. N by N, that's a state. N by R, R means the number of input. In control problem, normally you have only 1 input. But sometimes you have 2 inputs, 3 inputs, 4 inputs, 5 inputs together. So these formulations is applicable for multiple input problem. So R is the number of input. Now if R equal to 1 means you have only 1 input. Then this matrix size will be N by M plus R, this matrix, right? And this is on R by 1. And R and non is here. FC. FC is embedded here. So if I can solve the null space, then I should be able to form that null space basis vectors to compute FC. That's the tricks. Any questions? Oh, okay. So define. I have, say, gamma k. For each eigenvalue k, I can define a gamma k. And phi k equal to psi k, then fc psi k. So I define this gamma k equal to parentheses AC minus lambda KI, then BC. Then I have a phi K equal to psi K, then FC psi K. If I like that, and this gamma K is N by N plus R. R is number of import. So if R equal to 1, only one import, means N by N plus 1. So I have one column more. If I have 2 input, I have 2 column more. I have 3 input, I have 3 column more. And then again here. Okay. Now, key idea. Gamma K times phi K equals 0. So phi K is in the null space of gamma K. Any questions? So now we use single variety compositions. By the way, I also add a notes, some slides to show you how you pick the single variety composition, how you pick the null space basis vector, right? Did you see that? I think you did. Now, don't worry about this. A lot of number here, N minus R, Q. Don't worry about those. That's just some very, single variety. You count the single variety composition, how many non-single value you have. That I call the sigma K. So this is sigma K equal to UK. That's sigma K VK equal to UK. And this is sigma K 0. And then I have, by the way, there's a star here, VK star. I forgot the star here. All right. Now, star means transpose and conjugate. I forgot to tell you that this gamma K, define this gamma K, AC minus lambda K, because lambda is complex. So this gamma K normally is a complex matrix. This is complex matrix because lambda K normally is complex number. So this sigma, this the gamma K is a complex. However, single value doesn't matter it's complex or not. Single value is always real and positive. Even this sigma, even this gamma K is a complex matrix. The single value always real. But single vector can be complex. UK can be complex. VK can be complex. Sigma K will be real. So single variety composition, the good property is doesn't matter your single value, your matrix is complex or not, your single value always real and also positive. Cannot be negative. All right. Now, if you look at carefully here, the reason why I did not bother to partition UK, because we don't really need UK, we need only VK. Because the null space here, we need a VK. All right. So here I partition two pieces. One is a V sigma K, one is a V0K. The V0K means corresponding to this 0. Those 0 terms. About these 0 terms. All right. Now, if I keep moving further, we'll be able to find out is this gamma k, move this to the right hand, to the left hand side, move the v gamma k v 0k to the right hand side. That becomes this v sigma k v 0k. Now, by the way, when I move this one to the left hand side, if you recall the single variety decompositions, V and U, they are, we call unitary matrix, means what? Means their inverse is their transpose. For the complex, the inverse means the transpose and conjugate. All right. So if you look at this carefully here, from here, I move this one to the left hand side because what? Because I want to have this gamma k, 3k equal to 0. Now, if you go further, you find out gamma k v0k equal to 0. See, 0 vector, the 0 vector here. Gamma k v0k equal to 0 vector. This 0 vector is corresponding to that 0 vectors. N times n minus plus r minus q. That means this v0k not only, it may not only have only one column. You can have 2 columns, you may have 3 columns. In other words, your null space can be multiple dimensional. Your null space may not be only one dimension. So any vector in that null space, any vector in that null space can be chosen to be psi k. There are 3k here. I will give you an example later soon. All right. So how can I solve this null space? We must use single variety decomposition to do that. So before single variety decompositions are invented, this technique is not. This technique is not the. It's not available. Do you have any question about this? You gotta follow me on this. If you don't follow me on this, you get lost. If you get lost, means you cannot follow me anymore. All right, maybe let me do this. Maybe we come back later. Let us look at the example first. Maybe that's easier, right? I think so. I think that's probably easier to do this, because you might be confused by how come I have so many index here, index here. But the key concept is this null space is not necessarily only one-dimensional null space. What is going on here?
你去按前面抬头。
Oh,
No battery.
All right. Okay, I almost run out of power. So the key idea here is the V0K can be several different columns. They are not necessarily one column. It can be 2 columns, 3 columns, depending on the dimension of your null space. In other words, dimensional null space can be 1-dimensional, can be 2-dimensional, can be 3-dimensional, can be 4-dimensional. It depends on how many non-zero single values you have. Okay? If you have a multiple dimensional null space, that means good too, because you got so many different choices for your null space basis vectors. Okay? But normally, you really hard only if you have a single input, you have only 1-dimensional null space. That's normally. Okay. So here, I add CK here. Means any combination of V0K. Assume V0K has two vectors there. Any combination of these two vectors can be your null space vectors, right? Because you multiply CK, it doesn't matter you multiply CK or not, it's still 0. Except you multiply CK, this becomes a vector. This is the matrix, but this is a vector. All right?
CK is a vector.
CK is a vector. If this is 2 column, CK will be 2 by 1. If this is 1 column only, CK will be a scalar. If VK is 3 columns, CK will be 3 by 1. By the way, CK is a complex number. Can be a complex number because the V0K is a complex. This gamma K is a complex because your eigenvalue is a complex. So your gamma is a complex. V0K is a complex. CK can be complex, can be real. It seems very complicated, but it's not. When you come to the example, you will say, oh, wow, that's how come so powerful? All right, so I have an arbitrary vector. So that means I can choose any combination. Okay, so Vk can be V0K times Ck. So this is Vk can be V0K Ck. That means what? Vk is a unique. Vk is not a unique vector. Can we have all kind of choices? What does that mean is, this is Vk, not Vk. You have freedom to choose. This is Vk, and that's good part of it, because you have a good freedom to choose the Vk you want. All right, let us take 10 minutes off. I let you 10 minutes let you digest a little bit before I go further, because that's, there's a lot of theory here, but before I come down to the example, you will be confused. I know that too.